So we get an introduction to multivariate analysis, and now we're going to see how this actually works in practice. So this time we're actually not going to work on real data. I think the best way to illustrate it will be through synthetic data that we just simulate. And to simulate this data, I created this kind of simplistic causal model that explains how the data came about. You can see the graph here. Okay, so basically we want to model different, say, medical or lifestyle properties of individuals and like the ways that they can affect each other. So for example, we have a variable, sugar intake, which affects the body mass index of individuals, leading to maybe some people being obese. And we have smoking, which can affect lung cancer, or we have alcohol intake. And those three variables, the BMI, lung cancer, and alcohol intake, can affect the death of an individual. And then on top of that, we include two kind of generic variables, sex and age, which basically affect everything. So everything is affected by sex and age, both directly and also indirectly in some cases. Okay, so you can see like how things affect each other here. And that's like the ground truth, which we assume here. And we actually going to simulate the data according to this kind of causal diagram that we see here. Okay, so I wrote here a piece of code that will simulate this kind of synthetic data according to this causal model. And we're going to do that for 100,000 individuals. So we're going to have quite a large cohort. And OK. So to do that, we define two functions, which I'm going to explain in a bit. So we have translate to range, which takes some kind of raw values and make sure, just does some linear scaling to make sure that they will fall between some minimum and maximum value, just rescaling the values. So making sure that the minimal value will go to the new mean value and the maximum will go to the new max value. So simple linear scaling. And then we have another helper function, which is called top quantile to 1, which again gets some raw values and the percentage of top quantile that we want to turn into 1. And then what it simply does is taking all values that are like the highest value according to this quantile and turns them to 1 and all the rest to 0. So it does some kind of binarization of the data. So for example, if we give it 0.2, it will take the top 20% of the values, turn them to 1, and the lowest 80% it will turn into 0. Now, to make sure that the data we create is consistent, we initialize the seed like you saw in a previous bonus presentation. So this makes sure that every time that we run it, we actually get the exact same data, which is nice. It's nice when we actually try to simulate data. You don't want to be affected by all kind of random behavior. So if we comment it out, we can see that now every time that I run it, I get a different kind of data. But once it's included, it's actually deterministic, and it will produce the same data points every time. So we begin by creating an empty data frame without any columns, just indexing it, making sure that it has 100,000 rows. And then we start putting in columns for each of the variables. So for example, we take sex to be some random. So we simply use the roundin function to randomize 0 or 1s. So we say that 0 is female, 1 is male. So basically 50-50 chance to being a male or female. Likewise, with age, we take some random integer between 21 to 99. And again, uniform distribution, just any random age within this range. And now to model the sugar intake, what we do is we make it affected by age and sex, because we see in the graph that sugar intake is affected by sex and age. And the way we model that, we do some kind of linear modeling. We take minus the age. So we want to have a mild effect of age. So we say that, let's say, the older people are, the less sugar they consume. And again, we reduce the sex. So let's say that males consume slightly less sugar. But mostly just random. So we then, on top of that, we take some Gaussian random. with a standard deviation of 300. So we want most of the effect to be random because we say, OK, maybe sex and age affect to some extent sugar intake, but we don't think these are like very strong effects. So mostly random with respect to this kind of modeling. And then we do translate to range between 1 to 5. So we take the values and force them to be between 1 to 5. And we then round it and convert it to integer. We want it to be some kind of discrete step function. So it can be either category 1, 2, 3, 4, or 5. We don't want it to be fully continuous. OK, and then what you see again, you see what we expect. We get some number ranging between 1 to 5, saying like what kind of category of sugar intake this individual is. And for alcohol intake, we do something very similar. Again, we want it to be somewhat negatively correlated to age. So let's say that younger people drink more. And let's say that males drink more. And we also want it to be random to a large extent, but maybe to a lesser extent. So this time we want the age and sex to actually affect it more. And again, we convert it to some kind of discrete categories between 1 to 5. And we get the numbers. With smoking, again, it's dependent on age and sex, but mostly random. And again, this time it's binary, so we want to take the top 25% and say that there are smokers, and the rest are non-smokers. Okay, so we model it as some kind of binary thing. Now, BMI, we actually want it to be something continuous. We round it just to one decimal digits. And again, we want it to be dependent on age and sex and strongly dependent on sugar intake, but also having a large random component of things like other environmental or genetic factors, which we do not model. And lung cancer, we want it to be very strongly affected by smoking, but again, also containing some kind of random noise. And death is basically affected by age and sex as usual, and also like the 3 other variables, which we said, like the more BMI one has, the more likely they are to die, and the more alcohol they consume. And if they have lung cancer, it is very strongly correlated with death. And then again, we get something binary. Yeah.
Isn't it like double? When you say the BMI is related to age, sex, and sugar intake, but you already define the sugar intake related to.
Yeah, that's what I said. Like in causal diagrams, you can have direct effects, and you can also have indirect effects. So, in fact, it's very likely that that's like the way reality actually works. So we have some variables affecting other variables through different pathways. So sex could affect, let's say, BMI. It could affect it directly. It could affect it through sugar intake, through all kinds of other. It's called mediators. So you can have many different mediators, and it's not uncommon to have many complex indirect effects. So it does make sense. OK, and then we get like let's say that 20% of this population is dead. And that's basically it. So this creates this kind of synthetic data. And the nice thing about it is that it's completely synthetic. So we know exactly how we created it. And now we can run all kinds of analysis on that and see if the results make sense. Now that we know what we actually should expect of the data, because we know exactly what kind of causal relationships we have and what kind of causal relationships we don't have. OK, so let's begin with multivariate linear regression. So before actually doing linear regression, let's begin with a more simple kind of analysis. So let's begin by just plotting the data and see that it actually makes sense. So here we plot BMI as a function of alcohol intake. Now, to remind you, here we have BMI and here we have alcohol intake. They are not causally affecting one another, OK? So causally, they're unrelated, but they are confounded. So both of them are affected by sex and age. And if we take this kind of box plots view, so for each group of alcohol intake, we plot the distribution of BMI, you can see that we don't get the exact same distribution. So we get some mild differences. And we can even run a Spearman's rank correlation between these two variables, and you can see that we get a very mild negative correlation, but due to the large data set, it's very significant. Okay, so we get a very significant correlation, but here we know for certain that this is a spurious correlation. Okay, we know that it's confounded by sex and age. And I think this illustrates the kind of problem that you run into once you don't treat covariates properly. Okay, so to account for sex and age, we can run a multivariate linear regression, which is very similar to the way we ran simple linear regression, just we put in more variables. So again, we take BMI to be the y variable, and we take sex, age, and alcohol intake to be the x variables. We simply take the relevant columns from the data frame. We apply the ed constant, which, if you remember, is very important. And this gives us x. And like with two variables, we simply use the OLS class. We give y, we give x, we fit the model, we get the results. And now to get the p-values, we can use the model results dot p-values with respect to alcohol intake. And this will give us the regression p-value of alcohol intake under the null hypothesis that the coefficient should be 0. So in other words, what we spoke earlier, if we get a significant result, this means that we have a significant association between BMI and alcohol intake after accounting for sex and age. And you can see that we get a 0.28 p-value, which means it's not significant. So now that we actually account for these two variables, we actually get rid of this spurious correlation. And actually, the p-values would be a Pandas series that for each one of the variables that we have will give us the p-values. So we have the constant, which is just due to the ed constants, and sex, age, and alcohol intake. And you see that actually sex and age are significant even after controlling for the other two variables, as they should be. We know that they do affect BMI. But alcohol intake is not significant once we account for these two. And like with univariate analysis, we can use a summary to get the exact details of the model. And specifically, we can get some regression line if we want. So we can get the exact coefficient that it uses. So you can see the coefficient for each variable and all the other kind of statistics. Questions? Okay. Now, what happens if we do the same trick, but this time we want to test the association of BMI with sugar intake, not alcohol intake, after accounting for sex and age. So we basically do the same thing. We fit the model, we get a p-value, and you see it's basically 0. So it's super significant. And that makes sense because, again, according to our causal diagram, we know that there is a direct effect between sugar intake to BMI, even after accounting for sex and age. Okay, so as we expect, these two variables remain associated even after accounting for these variables. So it's quite an effective way to really discern between confounded and unconfounded effects, given that, of course, we know what to account for. And you can, again, see the figure and see that we have a quite strong association. So for each group of sugar intake, you can see the distribution of BMI, and you can see that it, in fact, increases as we expect. OK, now what happens if we include additional variables like alcohol intake and smoking, which are irrelevant? So in this case, nothing happens. It's still significant, as we expect. So of course, accounting for smoking, alcohol intake, all of those, that doesn't really change the fact that sugar intake affects BMI. We still have this direct arrow between them. Now, later I'm going to show you that it can lead to trouble if we account for things that we shouldn't account for. But for now, it seems to be fine. Okay, let's speak about logistic regression, which is really the same idea. Okay, so in this example, we're going to look at the association between alcohol intake to lung cancer. So again, you can see them here. So at least according to our simplistic model, we assume that there shouldn't be any causal link between them. So neither affects the other. But they are confounded by, again, sex and age. So let's see what happens. So we can create this contingency table that for each group of either people that have lung cancer or don't have lung cancer, you can see the percentage of each alcohol intake group. And you can see that there are some slight differences. I mean, it doesn't look like very substantial, but if, for example, we run a U-test and compare the values between each of these two groups, we can see that we still get something which is somewhat significant. And again, that's not surprising given that they are, in the end, confounded and that we have such a large cohort. So this is often called the too big to fail. Okay, we have such a large cohort such that even the slightest, smallest effect size would still be very significant. We have 100,000 samples.
Can you estimate what will be the result if you reduce it to 10,000, for example, or 50,000? I mean,
yeah, it's hard to tell. I mean, typically it tends to go exponentially with sample size. So increasing the cohort by a factor of 2 can actually lead to some power growth in significance. So it's very important. So larger cohorts really make a very substantial difference. But of course, the exact numbers depend on like the details. Okay, but again, we know it's a spurious correlation. I mean, if we just ran this analysis, we wouldn't know that. The reason that we know it is because we actually were the ones to create the data, and we know exactly what we should expect. So we know that sex and age should be confounders. And to account for them, we can simply use logistic regression, which works exactly the same like OLS. It has the exact same interface. So instead of using OLS, we use the logit class. Again, we give y and x. We fit. We get a p-value. And you can see it's not significant. It's 0.83 like we expect. So after accounting for sex and age, alcohol intake doesn't seem to change lung cancer distribution. Okay, and the reason we use logistic regression here is because lung cancer is binary. It's either 1 or 0. So it makes sense to use a logistic regression and not linear regression. And again, it has the exact same interface. We can see the p-values for each of the variables. And we can get a similarly looking kind of summary. Again, we can get the coefficients if we want. And again, now if we take something that actually should be, actually we do have causal relationships. So we know that lung cancer is in fact affected by smoking. So even though we include sex and age, we still get a super significant p-value like we expect. We know there is a very strong effect of smoking on lung cancer. And you can see that it actually works. Yeah?
but in the model results, p-values also sex is not.
Sorry? Why is sex not significant? Yeah, there could be all kind of, I mean, just because you have an effect doesn't mean you will detect it. It could be a very small effect. So we know, for example, that what we have here, lung cancer. So we probably took a very small effect size of sex on lung cancer. I don't remember the exact number. When we model it, you can see it has a very small effect. So it could be that it's somewhat swallowed within this model and you don't see it. Maybe if you increase it to 1 million samples, then it will become significant enough. Okay, and here too, if we include more covariates, so very often it won't matter. So again, we can look at the effect of on lung cancer of sex, age, smoking, and also some unrelated things which we know aren't confounders like alcohol intake and sugar intake. and it doesn't bother us. Okay, so still we get a significant p-value that we expect. Okay, so now let's speak about a scenario in which it actually does matter that we include additional covariates that we shouldn't, and that relates to the topic that is known as colliders. So again, let's begin with the simple example. Let's look at the association between BMI and lung cancer after accounting for sex and age. So we have everything here. We get a p-value. And again, to remind you, we know that BMI and lung cancer shouldn't be associated with one another after we account for sex and age. So this result makes perfect sense. We get something that is not significant as we expect. But then what happens if we also include death as a confounder? Now, if we actually look at the diagram, we see that death is definitely not a confounder, okay? So it doesn't seem like it should matter much. So it should be like including, I don't know, like something like maybe alcohol intake or smoking or other things which we know aren't confounders. So we can see here, now we run the same analysis, but also include death. But you can see that now something very strange happens. We look for the association of BMI and lung cancer after accounting for sex and age. So we know they shouldn't be associated with one another. We know there is no causal link between them. And everything that they do have, every association that they do have in common is only due to these two confounders. So why on earth, when we included death, did it make this strange spurious correlation then to appear apparently out of nowhere? This is very strange. And this is a very strange and very often neglected phenomenon, which is known as colliders. So what happens is that death is not a confounder, but it's not affecting the two variables. Rather, it is affected by these two variables. So both BMI and lung cancer, they affect death. By the way, it doesn't have to be a direct causal relationship. It could also be indirectly. It would work the same way. So once we have something that is affected by the two variables that we want to study, this is known as a collider. This is something that is affected by these two variables. And that's a very bad idea to try to include those kind of variables as covariates. Now again, it's very non-intuitive, but let me try to give you some intuitive explanation of why this happens. So we know that there could be multiple reasons for why a person would die. They could die due to lung cancer, or maybe having some overweight, or any other thing we included into the model. Now, in the general population, there isn't association between BMI and lung cancer, again, after accounting for sex and age. But if we specifically look at dead people, then this actually changes the situation. We know that if a dead person has a very normal BMI, then maybe this indicates that the reason for their death is the fact that they have lung cancer. So being dead and having a normal BMI indicates that there might be a problem with something else, like lung cancer. And vice versa, if we know that a person doesn't have lung cancer, maybe his death is explained by their BMI. But on the other hand, if we know that they do have lung cancer, then we don't need the BMI to have strange value. It's already explained away by the fact that they have lung cancer. Okay, so even though we don't have association between them in the general population, if we look at something that is actually affected by these two variables, we do expect this kind of association to appear. Another kind of toy example that people often use, and again, I think this makes it very clear what happens. This is a very famous toy example. So let's say we are interested in Hollywood actors, which could have different levels of beauty and talent. And whether they become celebrities is actually dependent on either their beauty or talent. So if we have a very pretty actor, they will likely become a celebrity, or very talented would also become a celebrity. But if we have someone that doesn't look that good and doesn't have talent, then they won't become celebrities. Now let's assume for the sake of this argument that in the general population we don't have any association between these two variables. So among all actors, there is no relationship between beauty and talent. But if we look at someone that we know is a celebrity and we know that they are not incredibly beautiful, then this indicates that they might be very talented because something needs to explain the fact that they are celebrities. And of course, vice versa. If we have someone that is not very talented, we can suspect that they might look very nice. So each one of them already can explain away the fact that someone is a celebrity, and we don't need a second one in order to explain that. So that indicates what happens when you take something that is not associated with one another in the general population, and then you account on the confounders, something that both of these variables actually affect directly or indirectly. And that's why colliders can be very dangerous. And what I said at the beginning of the class, so the strategy of, OK, let's just account for everything and control for every variable that we can possibly think about, is probably a very misguided kind of approach. And you actually want to be smart about it and take only things that you think are actually likely to be confounders and unlikely to be colliders, of course, depending on the domain that you study. So yeah, the bad news is that there is no silver bullet that you can use, which will always work. You need to use judgment and be familiar with the things that you actually try to study. But yeah, once you have this domain knowledge, I hope I convinced you that this kind of multivariate analysis can be very powerful tool to use. And by the way, I think I recommended this book previous week when we spoke about statistics. You have the Book of Why by Judah Pearl, which actually discusses this topic quite elaborately. So if you're interested more about all of these kind of confusing causal issues of confounders, mediators, colliders, I think this is actually a very nice source to read and to learn more about it.